Okay, so let's apply what we know about differential equations to discuss our models for population growth. It is required that we know how to solve separable equations to do this. So let's apply our separable equations technique to our two models of population growth. So let's look at the first model. It was the law of natural growth. Now we wrote down a solution before, but what we can do is actually solve it ourselves because it really was separable all along. So let's recall that the law of natural growth says that the rate of change of a population is directly proportional to the population itself. But this implies that dp over p is equal to k dt. In other words, we can separate the variables. Integrate both sides, we get the natural log of p is equal to kt plus c. Or if we raise e to the power of both sides, we get the absolute value of p is equal to e to the kt plus c. But this is just the same as e to the c, e to the kt. Okay? Now, the absolute value of p, remember, to solve an absolute value equation, this actually means that the inside of the absolute value is plus or minus that thing over there. And so what I could say is this implies that p is equal to e to the c, e to the kt, and the population is equal to negative e to the c, e to the kt. But on the right, this is impossible because all of this is a negative number, and you can't have a negative population, so let's just throw that out. So really, we're going to go with the model on the left. Okay, so this is what we want. Now, to actually find the constant, all we have to do is remember, so recall that if p of 0 is equal to, we usually call that p naught for initial population. This means that if we plug in a t of 0, we actually get, sorry, that should say p. We actually get a p equal to p naught. So coming back here, we're going to plug it into this guy right here. So on the left, we're going to plug in p naught, and for t, we're going to plug in 0. So what does that end up giving us? From that equation, we actually get that p naught is equal to e to the c. And so this means that p of t is equal to p naught times e to the kt. So this is our law of natural growth formula. This can be memorized, or you can just set up the differential equation and solve it on your own, right? It is not difficult. So another way that we could actually visualize this is called the relative growth rate. Okay, so what is the relative growth rate? So the relative growth rate of a population is the rate at which it's changing divided by its current population at that time. But remember, and let me underline that because this is a definition. But remember, if dp dt is equal to k times p, and this is just the given of the model, then that means if you divide both sides by p, you end up with this, which is a constant. And so, what does this mean? So this means that the law of natural growth implies that the relative growth rate of a population is constant. Okay, the relative growth rate of a population is constant. Okay, so let's go on to the next model. This is the more interesting one. So remember, this was model number 2. We call this the logistic model. This one we did not solve previously because we had no idea how to solve it with what we knew. So let me remind you guys of what is going on in the logistic model. P of t is equal to the population, and m is a constant which is equal to the carrying capacity. Think of it as the max capacity that can exist given the space that you have and the resources and all that stuff. Okay? So recall our setup. The differential equation was that dp over dt is equal to kp times 1 minus p over m. So this is our differential equation, and what we're actually going to attempt to do now is solve it so that we can come up with a general formula that works. Okay? So what is the solution going to be? I'll leave a space for the solution here. Let's go ahead and start the work on the next page, okay? We know that if we try to separate variables here, we actually can do that. All we have to do is divide both sides by all of the stuff with p's on the right. So let's go ahead and write that on the next page. We know that dp over p times 1 minus p over m is equal to k dt. And so this is separable, right? This is separable. So how do we solve it? We integrate both sides. Now, integrating these is not going to be easy. Integrating the right is easy, but integrating the left is not going to be easy. So what I'm going to do is I'm going to multiply the top and bottom of the left by m. And so let's work on the left-hand side here. If I multiply, so this is what we're working on. If I multiply top and bottom by m, it means I'm actually integrating by m over p times m minus p, and then dp. So what is this equal to? Well, I will skip all of the steps. I can tell you, though, that by partial fraction decomposition, this is actually equal to the integral of 1 over p minus 1 over p minus m. What is this equal to? This is equal to the natural log of p minus the natural log of p minus m. Okay, so all of what I just wrote is the left side, okay? But if you look at the right side here, the right side is extremely easy to integrate. That's just kt. So put it all together, you end up with the following. ln of, I'm going to go ahead and write it this way. ln of p minus ln of p minus m is equal to kt plus c. Now from here I'm going to be doing a lot of simplification. So if we multiply both sides by -1, we get the following. ln of, let me write it this way. ln of m minus p over p. Okay, I combine them using the rule of logs, and I'm also multiplying both sides by a -1. That's why I have this one on top. This becomes negative kt minus c. Now take e to the power of both sides, and we end up with m minus p over p is equal to e to the negative c e to the negative kt. This implies that m minus p over p is equal to plus or minus e to the negative c e to the negative kt. Now we're going to go ahead and actually call this guy, for simplicity, we're going to call this guy a. Notice that a could be any real number except for 0, because e to the c can never be 0. So I'll just say it's a, which is any real number, but also a is not equal to 0. What is this equal to now? Let's keep going. I'm going to take this fraction on the left and split this up. So we end up with m over p minus p over p, which is 1, is equal to a e to the negative kt. Okay, so this is what we get. And then from here, where do we go? I'm going to move the 1 to the other side. So this gives me m over p is equal to 1 plus a e to the negative kt. And then I'm going to take the reciprocal of both sides. This means that p over m is equal to 1 over 1 plus a e to the negative kt. And then finally, you multiply both sides by capital M. You end up with p is equal to m over 1 plus a e to the negative kt. Okay, so we are almost done here, except we introduced this new guy in here, a. We need to figure out what this a is. So how do we find a? We're going to use the same thing that we did before, which is we know that p of 0 is equal to p naught. So let's do this on the next slide. So if we know that p of t is equal to m over 1 plus a e to the negative kt, but p of 0 is equal to p naught, so this means we replace p of t with p naught, and on the right we have m over e to the 0 is 1, so we just get 1 plus a. So we get p naught equals m over 1 plus a. This implies, if we want to solve for a good way to do that is just to do cross multiplication. This means p naught plus p naught times a is equal to m. From here, solve for a. So we have p naught a is equal to m minus p naught. And then finally, this means that a is equal to m minus P naught over P naught. Okay. So we put things together. We have this and we have this. And so we go back to our original statement here. Our original statement where I was leaving space for the solution. The solution here is P of t is equal to m over 1 plus a e to the negative kt, where a is equal to m minus p naught over p naught. This is usually how we remember the solution. I do not recommend trying to solve this by hand each time. You really probably should memorize this solution. It just saves a lot of time when you're doing examples. So let's go ahead and do an example. So let's suppose population has initial population 500, and that it grows to 2,000 in 4 years. Okay, so this is a fact that we're just given in the problem, and we're going to do this in two different ways. So part A, I want us to find P of t if P follows the law of natural growth. Let's go ahead and do part A first, and then we will do part B, which is going to be to use the other model. So recall the solution is P of t is equal to P naught e to the kt. Right? This is the solution to the law of natural growth, okay? So from here, we just have to plug in what's given, right? So what's given in this problem? We know that the initial population is 500. This means that P, well, let me write it as P naught, actually. This means that P naught is 500. And it also says that it grows to 2,000 in 4 years. So this means that P of 4 is equal to 2,000. How do we use these facts? Well, first, take 500 and replace P naught with it. You end up with P of t is equal to 500 e to the kt. Now use the other condition to find k. We're going to plug this guy in now. What does this mean? This means that I can write 2,000 is equal to 500 e to the 4k. And then from here, we should be able to solve for k. So if we divide both sides by 500, we get 4 is equal to e to the 4k, or the natural log of 4 is equal to 4k, or k is equal to ln of 4 over 4. So this implies that P of t is equal to 500 e to the, I'm just going to take this k here and replace it with what we just got of ln of 4 over 4. We end up with 500 e to the, this is how I like to write it, t over 4 natural log of 4. So that is the answer to part A. Let's look at part B. Part B says, I haven't written it down yet. Part B says, suppose the population follows the logistic model. Remember, that's different. The logistic model with carrying capacity on 10,000. Find P of T. Okay. Well, we still have all the same facts, so let's write them down. Remember, P naught is equal to, what was it again? We said that it started off with 500, right? So P naught is 500, and we also know that P of 4 is equal to 2,000. So those two facts still don't change. Okay. Well, let's start by finding A. So recall earlier we wrote down what A was. A is equal to M minus P naught over P naught. Oh, I didn't write down the M here, but M is 10,000. So this is equal to 10,000 minus 500 divided by 500. Which is equal to 9,500 divided by 500. I believe that's 19. Let me just check on my calculator. Yes, that's 19. So A is 19. So we're ready to write our answer. P of T, remember, it's equal to M over 1 plus 19 e to the negative kt. So now we want to find k. So to find k, we're going to use this guy. Okay. So P of 4 is equal to 2,000. This means that 2,000 is equal to 10,000 over 1 plus 19 e to the negative 4k. So this is what we get, and if we can just manipulate here to solve for k, this means if we use cross multiplication that 1 plus 19 e to the negative 4k is equal to 10,000 over 2,000 is 5, or subtract 1 from both sides, we get this. Okay, or we get this after division, or take the natural log. Let me just break this off here. Or take the natural log of both sides and we get or divide both sides by negative 4, we get k is equal to negative 1/4 the natural log of 4 over 19. So what we just found is k, and so we can actually replace that into k right here. So let's go ahead and write our P of T. Let me back up here. We've got 10,000 over 1 plus, and then k, oh no, we have 19 e to the two negatives cancel out. So let me write this down. 1 plus 19 e to the, and I believe we have t over 4, right? Let me take a look one more time here. we have t over 4 natural log of 4 over 19. T over 4 natural log of 4 over 19. So this is our P of t. All of this is our population. We do have one more part to this problem. Let's go ahead and ask the following question. When, or let me write it this way. How long will it take for the population to reach 7,500 using both models? So this shouldn't be too hard. We just plug that in for P of t, right? So we set P of t equal to 7,500 and then solve for t. So let's start with model 1, the law of natural growth. So if we look at our answer that we got for the first one, where is it? It's P of t equals 500 e to the t over 4 ln 4. So we're going to substitute for P of t 7,500. So let's write that down. We have 7,500 is equal to 500 e to the, let me look one more time, t over 4 ln of 4. And now we just need to solve for t. If we divide both sides by 500, using a calculator here, I get 15. We end up with 15 is equal to e to the t over 4 ln of 4. Take the natural log of both sides. We end up with the natural log of 15 is equal to t over 4 natural log of 4. Multiply both sides by 4 and divide by natural log of 4. You get the following. T is equal to 4 natural log of 15 divided by the natural log of 4. So we got our answer. We could write this as the number of years. This is called an exact answer, so this is the exact answer. What is this approximately equal to? Because that's not a very nice number to look at. So if we want to approximate that, I'm going to write 4 ln of 15 divided by ln of 4. If I do that, I get 7.8 years. So this is approximately 7.8 years. This is how long it'll take to reach 7,500 if we assume the law of natural growth, meaning there is no max capacity. So let's try the other model now. So we're again going to set P of t equal to 7,500. So what does this mean? So let me write the logistic model now. We write 7,500 is equal to, now remember our other model is right here. We're going to write 7,500 equals 10,000 over 1 plus 19 e to the t over 4 ln of 4 over 19. Okay, what do we do from here? Again, use cross multiplication and also divide. We end up with 1 plus 19 e to the t over 4 natural log of 4 over 19 is equal to what? Divided by 2500, you end up with 4 over 3, right? If you subtract 1 from both sides, that ends up being 1/3. So you end up with 19 e to the t over 4 ln of 4 over 19 is equal to 1/3. From here, we're going to divide both sides by 19. This gives us e to the t over 4 ln of 4 over 19 is equal to 1 over 57. Take the natural log of both sides. We end up with t over 4 ln of 4 over 19 is equal to the ln of 1 over 57. Finally, from here, solve for t. You end up with t is equal to 4 natural log of 1 over 57 divided by the natural log of 4 over 19. This is how many years it takes. This is an exact answer. Or if we want to write that as an approximate answer, if I put it in my calculator, I end up with 10.4 years. So it does take longer for the logistic model population to grow to 7,500, and that's because it's getting closer to the maximum capacity of 10,000. So it makes sense that as we get closer to it, it's actually starting to grow slower and slower, which is why it added this extra few years. And that concludes the video. Thank you very much for watching.